Imagine time as an electric current, unceasing, invisible, always flowing forward in our experience, yet governed by laws that never insist on this direction. In 1928, Paul Dirac reshaped the course of physics with a single equation, as elegant as it was disruptive, forecasting antimatter and uniting quantum theory with Einstein's relativity. But if the rules beneath reality let time run both ways, why do we feel history pulsing only forward? The answer lies where mathematics collides with mystery. In 1928, Paul Dirac set out to solve a problem that had frustrated physicists since the birth of quantum mechanics. He asked how to describe an electron moving at speeds close to light, in a way that would satisfy both quantum theory and Einstein's special relativity. Earlier attempts, like the Klein-Gordon equation, could not account for the electron's observed behavior. Dirac's approach was different. He insisted on an equation that was linear in both space and time derivatives, so that time and space would be treated on equal footing. That demand led him to a new kind of mathematical object, the gamma matrices. These matrices, unlike ordinary numbers, do not commute, and their algebra encodes the geometry of space-time itself. The structure of Dirac's equation required the electron's wave function to have four components, a spinor rather than a single number. This was not a choice made for convenience. The mathematics demanded it. As Dirac worked through the consequences, he found that the equation automatically described a particle with spin 1/2. Spin, which had previously been added to quantum models by hand, now flowed directly from the algebra. The four-component spinor allowed the electron's intrinsic angular momentum and its correct magnetic moment to appear as unavoidable consequences of the theory. The unification was complete. The Dirac equation combined quantum mechanics, relativity, and the physical property of spin into a single tightly constrained mathematical form. The equation's symmetry, its respect for Lorentz invariance, was not just an aesthetic preference. It was the source of new physical features, revealed by the logic of the mathematics itself. But this same structure also brought with it a puzzle, the presence of negative energy solutions which could not be ignored. That challenge would soon demand a new interpretation of what the mathematics meant. Negative energy solutions haunted the Dirac equation from the start. The mathematics did not merely permit them, it insisted on them. For most physicists, these solutions seemed like an error, a sign that the theory had gone too far. But Dirac refused to abandon the structure. Instead, he proposed that every negative energy state was already filled, forming a sea so dense that only the absence of an electron, a hole, could be noticed. Such a hole, he reasoned, would behave as a particle with the same mass as the electron, but with a positive charge. He called it the anti-electron. This was not an idle speculation. The equation's internal logic left no escape. Dirac's commitment to mathematical elegance was unwavering. He once wrote, "It is more important to have beauty in one's equations than to have them fit experiment." For him, mathematical beauty was not a luxury. It was a guide to truth. In 1932, Carl Anderson, working at Caltech, detected a track in his cloud chamber that curled in the opposite direction from an electron's path. The particle had the same mass as an electron, but a positive charge. The positron, predicted by algebra, revealed itself in the real world. A line of abstract symbols had conjured a new form of matter. The positron's discovery was more than a confirmation of theory. It was a case where the demands of mathematical structure dictated what reality must contain. For Dirac, this was vindication. The universe, it seemed, was compelled to follow the logic of beauty. At the smallest scales, the equations that describe nature do not prefer one direction of time over another. Newton's laws, Maxwell's equations, and the Dirac equation itself remain unchanged if time is reversed, if every motion, every interaction were to run backward. In quantum mechanics, this symmetry is encoded as time reversal invariance. If the wave function of a particle evolves forward, the same rules allow it to evolve backward, provided certain quantities like spin are transformed accordingly. The Dirac equation, with its deep ties to relativity, treats time as just one coordinate among four, no more privileged than space. This symmetry is not a quirk or an accident. It is built into the structure of the equations. Schrödinger's equation, so central to quantum theory, is structurally invariant under time reversal if the complex conjugate is taken. The laws permit a film of microscopic events to be run forward or backward with no contradiction. Even the processes that create and annihilate particles, so central to Dirac's vision, follow rules that are nearly time-symmetric. Yet there is a subtle exception. In the realm of the weak nuclear force, certain rare processes involving subatomic particles, such as the decay of neutral kaons, show a slight preference for one direction. This effect, known as CP violation, was first observed in 1964. According to the CPT theorem, if the combined symmetries of charge, parity, and time are respected, then a violation in one implies a violation in the others. Still, these violations are minute, detectable only in specialized experiments, and they do not account for the overwhelming sense of temporal direction in daily life. The fundamental rules, then, are almost perfectly reversible. They describe a world where time could, in principle, flow either way. This raises a profound question. If the equations do not insist on an arrow, why does experience? Where does the direction, the current of time, truly begin? In the late 19th century, Ludwig Boltzmann faced a puzzle that still shapes our understanding of time. The equations governing atoms and molecules, he realized, do not care which way time runs. Yet every day, heat flows from hot coffee to cold air, never the reverse. Boltzmann introduced the concept of entropy, a measure of disorder, or more precisely the number of microscopic arrangements compatible with a macroscopic state. He showed that, statistically, systems are overwhelmingly likely to evolve from less probable ordered configurations toward more probable disordered ones. This is the essence of the second law of thermodynamics. In an isolated system, entropy tends to increase. On the scale of molecules, the underlying laws remain time-symmetric. A film of colliding particles could be run backward, and the equations would still hold. But if you start with all the air molecules in one corner of a box and remove the barrier, the odds that they will spontaneously gather back together are so small as to be impossible in practice. The direction we experience, the arrow of time, arises not from the microscopic rules, but from the overwhelming statistical tendency for entropy to grow. Modern cosmology adds another layer. Observations suggest that the universe began in an extraordinarily low entropy state. The past hypothesis posits that this special beginning sets the direction for everything that follows. As the universe expands and structures form, entropy increases, and with it the sense of time's current flowing forward. The laws themselves remain indifferent, but the boundary conditions set at the origin of everything give rise to the irreversible march from order to disorder. Boltzmann's insight, grounded in probability, explains why we remember the past but not the future, and why the current of time, though invisible in the equations, shapes every moment we live. Quantum mechanics and relativity, so carefully unified in Dirac's equation, resist a final reconciliation when gravity enters the picture. In the canonical approach to quantum gravity, the equations take a striking form. The Wheeler-DeWitt equation is written h psi equals 0. Here, the wave function psi describes the entire universe, not evolving in time, but fixed by a constraint. There is no external clock, no explicit time parameter called t. The equation is timeless. This stands in sharp contrast to our sense of flow and change. Some physicists propose that time might be recovered from correlations among quantum variables or as an emergent property of entanglement. Others search for patterns in the structure of the universe that could restore a sense of progression. Yet no consensus has been reached. The mathematics offers a static tableau, while lived experience insists on movement. The problem of time remains unresolved at the heart of fundamental physics. In physics, a current is not just a metaphor for flow, it is a precise, measurable quantity. The electric current, defined by I equals dq over dt, captures the rate at which charge moves through a conductor, but the idea of current extends far beyond wires. At the heart of field theory lies the continuity equation. The change in local charge density over time, plus the divergence of the current, always sums to zero. This expresses a deep principle: conservation. In four-dimensional spacetime, the current becomes J mu, a four-vector that unifies density and flow, treating time and space as partners. The mathematics insists whatever flows remains consistent. Time, too, can be seen as a kind of continuity. Events do not vanish or appear from nowhere. They move, connect, and conserve. The current of time, like electric charge, obeys its own law of continuity, unseen but fundamental. Physics still treats time as a parameter, not a flow, yet every second our experience insists otherwise. Researchers today confront the unresolved tension Dirac revealed. The universe's laws remain time-symmetric, even as entropy drives us forward. The future of physics may hinge on how we reconcile this silent divide.